When you type a prompt into a traditional language model, it operates on a very specific mechanism, predicting the next logical word. It acts entirely on instinct, firing off a linear chain reaction of tokens without a second thought. That rapid-fire approach works beautifully for writing emails or summarizing text, but it breaks down quickly when the model faces a complex math problem, a massive coding bug, or a physics proof. Guessing the next most likely word does not allow you to formulate a multi-step plan, and more importantly, it leaves absolutely no room to check your work for errors along the way. To solve that problem, researchers are designing models that do something entirely different. They are forcing the AI to pause and deliberate before it gives you an answer. This strategy is called test-time compute scaling. Instead of burning all the processing power up front when the model is first built, engineers are allocating massive amounts of processing power at the exact moment you hit enter on a prompt. By drawing on that extra energy, the model generates hidden internal logic chains, actively working through the problem in the background. This massive allocation of compute transforms the model's output from word-level prediction into active, verifiable reasoning. Standard reasoning usually follows a single trajectory, one straight path from the question to the answer, but prefix-level scaling takes that initial starting point and explores multiple different logical paths simultaneously. Using Monte Carlo tree search, the AI maps a complex decision tree from your prompt. It evaluates every branch step by step, scoring each intermediate thought. It ruthlessly prunes the dead ends and reallocates computing budget to the highest scoring pathways. All of this tree searching, scoring, and deleting happens autonomously in the background, long before you see the first word of the final response. By systematically exploring all the options and culling the bad ones, the system mathematically forces a higher probability that the final answer is correct. But building out those branches exposes a massive cognitive asymmetry in modern AI. It is computationally very easy to generate a complex idea, but it is incredibly difficult to verify if that idea is actually true. To manage this, the architecture often splits into two roles. A decomposer breaks your complex query down into smaller sub-questions, and a solver attempts to answer them. Without strict oversight, the solver might confidently build an intricate, highly detailed solution based on a completely flawed first step from the decomposer. Engineers introduce process reward models. The PRM acts as an internal critic, checking the logic of each intermediate step before moving forward. True reasoning requires teaching models to relentlessly critique their own logic at every single node of the tree. You might assume that giving the model more compute time guarantees a better answer, but AI can actually overthink a problem. If the compute budget is too large, the model will often second-guess its own correct intuitions, throwing out a perfectly good answer to go down an expensive, incorrect tangent. Developers use optimization methods like latent thought flow and adaptive early exits to cut the reasoning process off the exact moment a correct answer is verified. Managing that delicate balance between too little thought and too much is what allows these systems to operate effectively in the real world. Keeping track of the engineering making these systems viable is exactly why we built TechThemes10x.com, the best place to understand where technology is actually heading. When an AI can accurately verify its own work, the level of trust we can place in these systems scales up aggressively. Self-verifying tree search architectures finally allow models to execute long horizon tasks, building out solutions piece by piece, without needing a human to sit there and correct them. This translates to models capable of managing intricate codebases, synthesizing massive financial datasets, and navigating multi-step workflows, tasks where a single logic error which used to derail the entire process. This chart shows how task reliability smoothly increases as the compute budget grows. Because the model actively prunes its own errors, the reliability of the output scales proportionally with the amount of compute you allocate to it. For anyone using these tools, the required skill set is changing. Success will rely less on clever prompt engineering and heavily on how efficiently you can manage an AI's compute budget. Granting AI the ability to stop, search, and verify its own logic is the final threshold to true autonomous reasoning. To stay ahead of exactly how these systems are being deployed, subscribe to TechViews 10x.